Hi, in this lesson, we'll look at informal code analysis. Throughout this course, we've spent a considerable amount of time developing algorithms. Algorithms are a step-by-step process that solves a problem. Many, if not all, of the programs that we have developed are considered algorithms because they solve a problem. We also use algorithms in our daily lives and don't even think about it. Most of the tasks that we perform on a daily basis are based on a routine and have procedures that we follow so that we can complete them as planned. Making a PB&J sandwich or reading a book are examples of practices that we do that have a procedural, step-by-step nature. In order to best create and use algorithms, we need to think about what makes a good one. Before going to the next slide, make a list of criteria that you think makes a good algorithm. In order to make a good algorithm, we need to make sure that it is functionally correct, efficient, and easy to understand. Did you come up with these? Did you think of any that aren't on the list? We will look at the correctness and efficiency in this lesson, with a major focus on efficiency. When creating algorithms, they should work as intended or specified. Take a look at this code segment. Does this work as intended? In this for loop, we needed to loop through 100 times, but the for loop only iterates 10 times. This program does not solve the problem correctly and thus is not a good algorithm. To make this a correct algorithm, we need to alter the state of the for loop so it iterates through 100 times. Besides correctness, algorithms also need to be efficient. Efficiency is important because it affects program speed and program cost. Let's dive into what that means. In order to understand efficiency, we need to understand how a computer reads programs. When a computer program or file is run, it uses CPU processing time. The CPU, or Central Processing Unit, is the electronic circuitry in the computer that carries out instructions. The processing time is the amount of time the computer spends, in seconds, on processing or reading the program's instructions. This is important because a computer has a limit to its CPU usage at any given time. The usage refers to the percent of the CPU that is currently being used to run and process computer programs. We can think of the CPU as a brain, or a container that is capable of processing and reading computer programs. When an application, like Chrome, is opened and actively running files and programs, it takes up part of the CPU usage based on the CPU processing time that each file or program requires. When we run lots of programs at once that are all actively providing instructions to the computer that need to be processed, we reach the upper limits of the CPU's processing power, which can sometimes cause slowdowns in our computers. This is why it is good to close applications that aren't being used. The more efficient a program is, the less processing time it requires to run. The faster that programs can be run often reduces CPU usage, making your computer faster and less likely to experience slowdowns. We can actually monitor how our computers are using CPU processing time and usage. This can give you an idea of which programs are taking a substantial amount of processing power to run, and which to close when you want to run others more efficiently. On Apple computers, you can view this by going to the App Activity Monitor. On Windows, press Ctrl plus Shift plus Escape to launch Task Manager. Then click the Processes tab and choose Show Processes from All Users. And on Chromebooks, you can go to the Chrome browser and find the information in the Task Manager. The speed of the program also has a substantial impact on the cost of the program. When you click on an activity on CodeHS or any other site, you are actually sending that information over to an Amazon server or external computer that then executes a series of programs based on your action. The server then runs a program that software engineers at CodeHS wrote to save your code and send that same code to your teacher's grading queue. Because servers take up a lot of space and electricity, most companies don't actually own their own servers, but rather rent them from other companies. These servers cost money to run and often change in price depending on how much CPU usage the servers use. limiting the processing time that servers have to spend reading and interpreting programs can reduce the amount of money that companies spend on renting servers and using CPU processing power. We can thus define an efficient algorithm as one that makes economical use of CPU time and memory. When considering whether or not an algorithm is efficient, we want to ask the question, how long does it take to perform a certain task, and is there another approach that will get to the result more quickly? Factors that affect runtime efficiency are unnecessary tests, excessive rearranging of data elements — this part will make more sense when we cover data structures in another unit — and redundant computations, especially in loops. Given these questions about efficiency, let's explore a couple of algorithms to see if we can figure out the most efficient one. We want to figure out if anyone else in a room has the same birthday as you. Which of the following algorithms is the most efficient? In this algorithm 1, you say your birthday and ask if anyone in the room has the same birthday as you. If anyone has the same birthday, they say yes. In algorithm 2, you tell Anika your birthday and ask if she has the same birthday. If she says no, you tell Matt your birthday and ask him if he has the same birthday. You repeat this process for each person in the room. In algorithm 3, you only ask questions of Anika, who asks questions of Matt, who only asks questions of Isabel, and so on. You tell Anika your birthday and ask if she has the same birthday. If she says no, you ask her to find out if Matt has the same birthday. Anika asks Matt and tells you his answer. If his answer is no, you ask Anika to find out about Isabel. Anika asks Matt to find out about Isabel, etc. The most efficient algorithm in this case is the first. This is the most efficient because it requires us to ask the question one time to everyone at once. Compared to the others, it will take the least amount of time. For the sake of this class, and with programming in general, it's important that we are able to measure or make an educated guess about how much time it will take to execute an algorithm. This will make it easier to compare alternative approaches. In general, it can be very difficult to predict the speed of an algorithm because it relies on a series of factors that are hard to calculate altogether. Because of this, we need a machine-independent way to try to estimate the speed of an algorithm. A basic approach that we can take is the statement execution count. This suggests that we can count the number of instructions that algorithm has to execute. Once we know how many times a piece of code executes, we can have a relative way to compare two or more algorithms for efficiency. When we say executed statement, that can refer to a series of different actions, such as assigning a variable a value or performing an arithmetic operation. Let's take a look at an example of a statement execution count. When this file is read, the first line of code is given to the CPU as an instruction and is executed one time. This means that the execution count at this point is 1. The next line of code is also an instruction to assign n the value of 10 and is executed once. The execution count is now 2. The third statement that is evaluated is part of a for loop. This executes n number of times as the for loop goes from 0 to n. We will add n to the execution count. Lastly, the print statement is executed once, so we add 1 to the execution count. In this example, the execution count for the program is 3 plus n, where n is the value initialized in the for loop. In this case, n is 10, so the program's final execution count is 13. While this program was fairly straightforward, adding control flow statements to programs can make this process more difficult, as they often iterate or change the sequential nature of programs. For programs with conditional statements, only one of the statements will end up executing, as the condition will either be true or false. Thus, the count should include one of the two statement counts. For loops, as we already saw, have programs repeat the same code a fixed number of times. If a for loop follows a standard ++ increment, we can actually calculate the execution count. In this general formula, the execution count for a for loop is n minus initial. We can subtract the value of initial from n to find the execution count, as the total number of iterations is the difference between these two values. As we can see in this chart, if I is less than 10 and I starts at 0, the total iterations will be 10. If there are nested for loops in a program, the execution count is similar to that of a regular for loop, except the inner for loop execution must be multiplied by the execution count of the outer for loop. As we can see in the table, if the value of n is 10 and initial is 0, and m is 5 and init 2 is 0, the total execution counts for that sequence will be 50, as the outer loop will iterate 10 times and the inner one will iterate 5 times each iteration of the outer loop. Comparing execution counts between algorithms is one way to determine whether or not one algorithm is more efficient than the other. Generally, we can associate the algorithm with the lower execution count as the algorithm that is more efficient, as it takes less lines of code to process. Now that we've learned how to calculate execution counts, let's try some practice problems. For this algorithm, what is the execution count? The execution count is 6. Each time the loop executes, n is divided by 2, so the loop will produce output when n is 50, 25, 12, 6, 3, and 1. The final value of n will be half, which is 0, because n is an int, and the test will fail. On to the next practice problem. What is the execution count for this algorithm? The execution count for this algorithm is 9. The for loop is supposed to iterate 10 times, but during the third iteration, when I equals 2, the value of I is increased to 3. On the next increment, the value goes from 3 to 4, skipping the third iteration through the loop entirely. This is an example of how the I variable can actually be manipulated within the for loop. For the last practice problem, we are going to look at two algorithms that do the same thing and see which algorithm is more efficient. This algorithm iterates through a string and determines if the character key is a character in the string. Can you figure out which one is more efficient? The correct answer is the one on the left. Let's explore why. The break statement in the code actually stops the for loop from running once the key in the string is found. If we were to use the string codehs and look for the key E, we would only have to iterate through 4 times before we would find the value and break from the program. The algorithm on the right, however, would iterate through the entire word even after the value has been found. That means the execution count would be 6, making this algorithm less efficient than the one on the left. Now that you've learned about informal code analysis, let's get some practice in the CodeHS editor.